Lecture 2 covers sections 1.7 through 1.11. At the end of today's lecture, you should be able to recognize the units of pressure and formulate the expression for pressure. You should be able to identify the components of energy, including the internal, kinetic, and potential energies. You should understand the difference between energy and specific energy. You should understand the equality of temperature and how it pertains to the zeroth law of thermodynamics. And lastly, you should be familiar with SI temperature scales, how we express temperature in both degrees centigrade and degrees Kelvin. For us to begin, pressure is defined as the force per unit area. Force is mass times acceleration and has units of newtons, and area has units of meters squared. The unit for pressure is a Pascal. Now, we assume that pressure acts uniformly over a given area, and that the pressure within a gas or liquid is going to act uniformly over the surface containing that gas or liquid. That is, when we have a fluid, it is going to be in mechanical equilibrium. The pressure is uniform throughout. Unlike fluid mechanics, we are not going to worry about the variation of pressure with respect to depth of our fluid, for most of the systems we analyze are relatively small scale. Now, the force produced by a pressure within a fluid is simply that pressure times the area on which it is acting. That is, force is equal to pressure times area, and that has units of newtons. Now let us look at an application of Pascal's law, where we have an incompressible fluid, i.e. a hydraulic fluid that's constrained between two piston cylinder devices. Our hydraulic fluid is indicated by red in the diagram below. An incompressible fluid means its density does not change with respect to a change of pressure. That is, if we increase the pressure, our density is going to remain constant. Say we want to determine the force, F2, that the second piston generates based upon the input, F1. Now in the schematic below, we have an air compressor that is pressurizing air. This pressurized air is going to act on piston 1, which has an area A1, which is going to generate some force. There's going to be a pressure existing within our hydraulic fluid that then is acting on piston 2 that has area A2, that results in the generation of a force, F2. For us to begin, the force acting on our first piston, F1, is equal to P1A1, or our pressure acting on that piston is our force F1 per A1. Now the pressure within our hydraulic fluid is equal. That is, the pressure everywhere within our hydraulic fluid is going to be described by P1. Thus, the pressure acting on our second piston, P2, is identically equal to P1. The force generated by our second piston is P2A2. Now, if we substitute in P1 for P2, we see that the force generated by piston 2 is equal to the force acting on piston 1 times the ratio of the areas of piston 2 per 1. We see we have a force multiplier. That is, if A2 is greater than A1, F2 will be greater than F1.